Okay, right, this should work. Just give it 15 seconds just to check. It's a 15-second delay. Hello. Okay, so that seems to be working. So let me mute that. Okay, so welcome to those on the call. Welcome to those watching the live stream on YouTube. This is a Socratic seminar. We haven't done one of these for a while, at least online. But let me share my screen just so I can say which. Seems to have changed since last time. Apologies for the delay. It's not letting me share my screen. Okay, well, I'll try and work this out while we do intros. Okay, so this is a Socratic seminar. We're going to be discussing MuSig2, and we'll move on to adjacent topics such as Frost and libsec-p later. We have a few people on the call, including Tim. So if you want to do short intros, you don't have to, but if you just do a short intro for the people on the call, I'll try and sort out this shared screen as you do those intros. So we'll start with you, Tim.
Yeah, hi. Thanks for having me, by the way. Yeah, so I'm Tim Ruffing. My work is at Blockstream. I am an author of the MuSig2 paper. I guess that's why I'm here. In general, I work on cryptography for Bitcoin and cryptocurrencies, and in a more broad sense, applied crypto. And I'm also a maintainer of the libsec-p library, which is a Bitcoin core cryptographic library for elliptic curve operations.
Great. Anybody else? You want to do an intro, Elizabeth?
Sure. My name is Elizabeth Kreitz. I'm a postdoc at the University of Edinburgh, and I work on very similar research to Tim, and I also work on the Frost threshold signature scheme, which I'm sure we'll talk about at some point during this, but yeah.
Cool. Anybody else? Almost got this shared screen working. No one else wants to do an intro on the call?
I'll just say hi.
Yeah,
I'm Nigel Sharp. Bit of a newbie, software engineer, Bitcoiner, sort of turned into a bit of programming. So just listening in really and on the call just in case I have any questions.
Cool. Anybody else?
Well, hi. I would just say hi as well. I'm Manish Garg. I'm just probably new and still learning, and that's why I'm interested to listen to this. So not sure I would have many questions, but yeah, thanks for arranging this, and yeah, looking forward to learn and understand.
Hi, and I'm Grant, excited about MuSig, and I may have a couple questions later on, but I think I'll mostly just observe it for the moment.
Okay. So I think my screen is sharing correctly. Right. So the intro that I skipped before. So this is a bit devs. It's a bit different to. There's a lot of bit devs all over the world. In various cities, there's a list there. If you can see my screen. This is going to be a bit different in that we're going to focus on one particular topic, which is MuSig2 and libsecp. And also we're going to assume a base level of knowledge from a Socratic kind of presentation Tim did a couple of years ago. So this isn't going to be an intro. So if you're looking for an intro, this won't be for you. But anyone's free to listen in and participate and ask questions. Where we left, so the Socratic we did with Tim 2 years ago, this was before bit 340 was finalized. This was before Taproot was activated. So this was before sure signatures were online and active on the Bitcoin blockchain. I suppose like first question, like bit 340 related, Tim, has anything in bit 340 been a disappointment or problematic or caused any challenges with any future work? Like it's always very difficult to like finalize and put something in stone and put it in the consensus rules forever, especially when you don't know what's coming down the pipeline in terms of other projects and other protocols, other designs. Like the only thing I've seen, you can tell me if there's anything else. The only thing I've seen is the X-only pub keys for the T-level code. But perhaps you can, yeah.
Can you repeat? I didn't understand that point. Sorry.
The choice of X-only pub keys. In bit 340, that's like had a complication for a covenant opcode that is, I mean, it's currently designed, but that's the only thing I've heard from bit 340 that has posed any kind of disappointment. But yeah, go for
it. I think that's the maybe the main point. Yeah. So we have so first of all, BIP 340 is the Schnorr signature BIP for Bitcoin. And one special thing about the way we use Schnorr signatures in Bitcoin is really that we have X-only public keys. What this means is that so if you look at an elliptic curve point, there's an X and a Y coordinate, so there's 2 coordinates, and if you have the X coordinate, there's an echo, I think. So if you have a X coordinate, you can almost compute the Y coordinate up to the sign, basically. So for each valid X coordinate, there are 2 Y coordinates. And that means that if you want to represent that point or store it or make a public key out of it, you need the X coordinate and you need one bit of the Y coordinate. And now what we actually did in the BIP here in our design is we dropped that additional bit. The reason is that it's often encoded in a full byte, and maybe you can't even get around this. So this basically saves one byte in the end, brings down our public keys from 33 bytes to 32 bytes, which sounds good, and it's really like it's just one byte or one bit, but I think it's a good idea to squeeze out everything out of layer 1 so as much as we can, right? Because space is very sparse there. So this was the idea, and it turned out that there's a nice blog post by Jonas. And this blog post explains that this is actually not a loss of security. So even though we drop a bit in the public key, it doesn't mean that the scheme becomes a bit less secure. It's actually the same security, and that's kind of explained in this blog post. Though it turns out that if you just want to do Schnorr signatures on Bitcoin with normal transactions, then it's pretty cool. It saves space. If you want to do more complex things, like for example MuSig or other complex more complex crypto, then this bit is always a little bit a pain in the ass. So you can always get around this, but whenever you do advanced stuff like tweaking keys, and then a lot of schemes involve tweaking keys. I mean, even Taproot itself involves tweaking, and then MuSig2 as key aggregation, and maybe they get another form of tweaking and so on. You always have to implicitly remember that bit because it's not explicitly there. You have to implicitly remember it at sometimes, and this makes specifications, let's say, annoying. I don't think it's a problem for security, but for engineering, it's certainly annoying. So in hindsight, it's not clear if you would make the decision again. I think I still think it's good because we save a byte, but you can also say, well, the increased engineering complexity is not worth it. And at this point, I could really understand both points of view, I think. So that's the one thing about X-only keys. And and you mentioned one thing on the mailing list, I think on Bitcoin Dev, where there was a suggestion by AJ for a new Bitcoin opcode that would allow a lot of advanced constructions. For example, I think this was about coin pools, right? We kind of have a shared UTXO between a lot of people, and also there the fact that we don't have the sign on, so the sign of the elliptic curve point of the public key would have created a problem there, because you kind of need the sign when you want to do arithmetic, right? Because if you want to add a point to another point, say a plus b, then if b is actually minus b, then it doesn't work out really, because then you're not adding but you're subtracting. This is the basic problem there. And there were some ugly workarounds proposed, and I recently came up with a better workaround that's still ugly, but I think not as ugly as the other ones. So this again shows that I think in the end this is all of it's just an annoying thing. I think it's we can always deal with this X-only keys, and they still save space then, but sometimes they're annoying. The only hope is that we can hide all the annoying things in pips and specification and libraries, so that actual protocol developers don't need to care too much about this. But
Yeah, so I think it was CoinPool was using this particular covenant opcode, but it's a complication for the covenant opcodes, tap, leaf, update, verify.
Yeah, right.
And then various things are looking to whether they'd use it if that was ever activated on the Bitcoin blockchain.
And maybe another, and by the way, like I was speaking a lot now, right? So
no, it's fine.
I think the point here is that this is super interactive. So
absolutely.
Please chime in.
Questions, comments, or anything that's confusing, please interrupt. But that's the only thing that's come to light regarding Bit 340 that has been.
Mostly I would say. So the other thing, that's not really a pain, but we're just working on a tiny change. At the moment, the message size is restricted to 32 bytes, so you can sign only messages that are exactly 32 bytes, which isn't really a problem in Bitcoin because we anyway pre-hash messages and then they are 32 bytes. But it turned out that some people would like to see this restriction lifted, and now we're working on a small update such that you can that basically allows you to sign messages of arbitrary size. But this is really just a tiny detail. In the algorithm works just that we specified it to accept only 32 bytes, and just you need to drop this check, and then everything is fine basically.
Okay, cool. So that's Bit 340. I just thought we'd cover that because before it wasn't active on chain, now it is. So hopefully that'll be the only thing that comes to light, Bit 340 frustrations. Let's go on to MuSig2. I have a bunch of links. There's some transcripts Tim Jonas did. So I thought I'd start with, just like try and do a basic history. The first paper I found was this Bellar and Nevin paper when they tried to do multi-sig, like aggregate, key aggregation, multi-sig type stuff. This, I was having a conversation yesterday. This, I don't know what the motivation is for this. Like before Bitcoin and before blockchains, like what were people using multi-sig for? What use cases were there where there's so many signatures being flying around? And not only that, but also wanting to have multiple people signing, and then on top of that, wanting to aggregate it to either get the privacy or the space benefit. So is it just a case of academics just like pursuing their interests and not really worrying about the use case, or is there a use case out there that people actually wanted this back now?
I mean, you can have a look at the paper, right? If they if they have a use case.
I don't think there's much about use cases.
No. Yeah. So I think blockchain and cryptocurrencies and Bitcoin changed cryptography a lot, in the sense that a lot of things were brought from theory to practice, I think. So cryptographers were always busy with ideas and schemes, but no one really deployed the advanced stuff. Of course, we always had encryption, we had TLS or SSL, we had signatures and certificates also used in SSL or TLS. So we had the basic stuff like encryption, secure channels, signatures. But almost everything beyond this simple stuff wasn't really used anywhere in practice. I mean, it was proposed in papers, and there were, great ideas. But in that sense, really, I think, cryptocurrencies have changed the entire field. So I think back then you wrote a paper and you hope that maybe someone will use it in 10 years. And nowadays it's sometimes you write a paper and you upload it on ePrint and it's not even peer reviewed and people will implement it 2 days later. So it's actually too extreme sometimes. I'm not sure what Elizabeth thinks, but I think that's just my impression.
Yeah, I would say that given that this paper was 2006, right? So I think people were starting to, around that time, this is my perspective because I work on anonymous credentials, but I think that was quite popular in the kind of like 2001 to 2006, like kind of pre-Bitcoin era. So I imagine that some of the motivation would have been distributing trust for certificate authorities. But I don't know. I think they do say that in this particular paper as a motivation. But nobody, as far as I know, nobody actually like implemented this.
Yeah, and I think back then, from a practitioner's point of view, I guess even if the goal is to distribute trust, right? You could have just have a simpler construction of multi-signatures where just you have multiple public keys and multiple signatures. And for CAs, maybe that's just good enough. And I think this really becomes interesting when you have things like key aggregation and have combined signatures that are as large as normal signatures, because space on the blockchain is so expensive. I think this is what makes it interesting to implement something like this, because in the end it's in all these multi-signature schemes, the modern schemes, in a sense, they are all interactive. So interaction is annoying. You have to send messages around and so on. And I think if you don't need to care about every byte on the blockchain, maybe it's just not worth it.
Yeah.
Yeah, I suppose the challenge would be like, would they need privacy in that multi-sig setting, or would they be motivated by the space savings? Like, why can it just be like 5 signatures? I suppose would be the challenge. I can't really see why
I
they
think
have that motivation.
And they don't have. I'm pretty sure I should know. This paper doesn't have key aggregation, I think.
I think it does. I think that was one of the. I think this was the first paper that had key aggregation, actually.
Oh, I should know. Let's
Well,
check.
it's got a
Let's check.
section.
Come on.
Yeah,
It's got a
because they
section on rogue key
yeah,
attacks.
because they had
Okay.
the first idea to avoid the rogue key attacks, right?
Yeah, but doesn't mean that you can still have
I'm
rogue
pretty
key
sure-
attacks even if you don't have key aggregation, right?
I'm pretty sure.
you-
Yeah, no, but I mean, I think that was the thing, was how to aggregate keys without the rogue key attacks.
Let's have a look. Maybe
Yeah.
the section. I don't know. Let's have a look at the syntax.
Do you want me to go to then? Where do you want me to go in the paper?
4.
I mean,
section.
I don't understand if it's talking about rogue key attacks. That is surely key aggregation, no?
But it doesn't need
It doesn't.
to.
It doesn't have to be. So you can
Yeah.
have.
I mean, you could do it internally, right? So.
Yeah, so you could just prove possession of your secret key, and then you can just multiply the keys together. But I think the interesting thing was that they were trying to not do that and have a key aggregation mechanism that still held without being susceptible to that.
Yeah, but maybe go to section 5. Then.
Also, I think this was one of the first papers that abstracted the forking lemma from being a scheme specific type thing to like a general.
A little bit more down. Stop. Yeah. Right. Do you see they just have a key generation algorithm? They don't have a key aggregation algorithm. Of course, during signing, they kind of aggregate keys.
Right.
But you couldn't use this, for example, for something like Taproot, because there's no. This just from the API, it doesn't give you a way to get a combined key.
Yeah.
This is what I'm saying. That they still can have rogue key attacks, because in signing you still add up keys and then you can get rogue key attacks, and need to be careful to avoid this.
So they didn't have the like how do they aggregate the keys actually? I'm really curious.
They don't, because verification takes all the public keys as input.
Oh, it does. Okay.
Yeah.
Oh, I thought that was one of the main motivations of this, but
no, I think this was then MuSig2 was the first
the first one. Okay. Yeah.
First that solved that problem. At least I mean it was there for BLS, I guess, already, but at least for
I think this paper is also like
a
good reference for like I was saying, the transition for the forking lemma, right? Because there was kind of a different forking lemma for every scheme that you wanted to prove, and I think this one abstracted it away from like something being like specific for a signature scheme. And I don't know, maybe I'm getting all the papers confused, but I seem to remember that being, because this is always the one that's kind of referenced as like the change in the forking lemma.
They say it's a general forking lemma, but my impression is that it's still not general. I mean, almost every paper needs
a new one.
Needs a new one. Yeah, it didn't really work out.
Yeah, no, that's true. Well, but it separated it from being like it made it a kind of an abstract algorithmic lemma versus being for like a signature scheme or something. But yeah, no, you're right, because you end up needing a new one every paper anyway. But that's kind of like the main contribution, I guess, that I see from this. If I'm remembering this paper correctly, that is. Which is a big if.
Okay, so move on to MuSig2. So MuSig2 addressed the rogue key attack because that was well known, but has this problem where you had parallel sessions, parallel signing sessions, and you could get a forgery if you had a sufficient number of parallel signing sessions, right?
Yeah, yes and no. So I mean, first of all, music. If you're looking from the Belar-Nevin to
okay, but let's go Belar-Nevin, then insecure MuSig2, and then secure MuSig2.
Right. So the innovation then of MuSig2 as compared to Belar-Nevin was now really that you have key aggregation. So you really have an algorithm, a public algorithm where you can get all the keys and aggregate them. This didn't exist in Belar-Nevin. But yeah, the first version of this, or the first version of MuSig2, it sounds bad, right? So I mean the first upload on ePrint here had a flaw in the proof, and this actually turned out to be exploitable. So there was really yeah, the paper was just, or the scheme was just insecure in the first version.
And then there was the fix. So this is committing to nonces to fix the broken MuSig1 to get to secure MuSig1, right?
Right. So they started with a 2-round scheme, and this 2-round scheme wasn't secure. The problem is that if you're the victim and you start many sessions, many parallel sessions with a lot of signers, then it turns out that, I don't know, if you start 300 sessions in parallel, then yeah, the other guy should get only 300 signatures, but it turns out it can get 301 signatures. And the last one on a message totally chosen by the attacker. So this was problem. This was the attack.
Was there a particular number of signing sessions that you need to be able to have to be able to get that forgery, or is it just a number plucked out of anywhere?
You need a handful, but the security goes down pretty quickly. So I think that there are two answers. So with the first attack discovered with Wagner's algorithm, there it's really, I think it goes down pretty quickly. So at around 100, I've never implemented it, but around 100, I think it's doable in practice. And if you have a powerful machine, a lot of computation power, maybe even much lower, I don't know. And recently there was a new paper that improves this attack to super low computation. But there, I think you specifically need 256. So if you have 256 sessions, or maybe 257 or something like this, in this order, then the attack is suddenly super simple. It's like, yeah, probably you could do it on your pocket calculator if you spend half an hour. Yeah.
And one thing you haven't really gotten, neither you or Jonas, in the presentations you've done so far, for good reason probably, you haven't really discussed in depth the different security proofs. I think in one you would so my understanding are there's 4 different security models for security proofs. There's random oracle model, algebraic group model, one more discrete logarithm, and then algebraic one more discrete logarithm, which is weaker than the one more discrete logarithm.
Yeah.
Yeah, can you dig a little bit deeper into that? Because I was getting confused.
I can try, and a little bit can chime in whenever I'm talking nonsense. Which I hope I don't, but no, it's just, let me think about how to explain that best. So first of all, I think we need to differentiate between models and assumptions. Though they have some things in common, but there are different beasts. So in cryptography, we usually need some problem where we assume that it's hard to solve. For example, in this case, the most fundamental problem that we use here is this discrete logarithm. Right? If a public key is g to the x, and you see the public key, it's hard to compute x just from g to the x, but the other way around is easy. And other assumptions that we typically know are factoring. It's easy to multiply large numbers, but it's hard to factor them again. For MuSig, we need a special form of this discrete logarithm. So the discrete logarithm assumption then is just what I said. It's an assumption that says it's hard to, given g to the x, it's hard to compute x. And the reason why I call this assumption is that it's really just an assumption. We don't know. We can't prove this. So this is not covered by the proof. people have tried for decades to do this, and they failed. So we believe it's hard. This sounds a little bit worrisome, but in practice, it's not that much worrisome, I think, because well, yeah, all cryptos build on this, and usually the assumptions don't fail. Or you can ask, okay, maybe there's a quantum computer soon that will compute D-logs. Okay, maybe, but let's not talk about this now. That's another story. So and here for MuSig we need some special form of this discrete logarithm problem, which is called one more discrete logarithm problem, and that basically yeah, it's a generalization. So we're the normal problem is just given g to the x, compute x, and here it's like, okay, I give you something like 10 g to the x with different x's, and I give you an how does it work? I give you now oracles, so I give you a magic way to compute 9 of these discrete logarithms, but you have to solve all 10. So it's basically you always need to solve one more than I give you a magic way to solve it. This is one more DL.
Okay.
And
this, yeah, go for it.
Yeah, just or go ahead.
I was just going to say, so the security proof for, so there was an incorrect security proof for the broken MuSig1 that was based on one more discrete logarithm, right? So is that the one more discrete logarithm model is no, that's a normal model for a security proof. It was just that there was a problem with the scheme, right?
Yeah.
Okay.
So in the theorem's security theorem would look like, okay, if OMDL holds, and so if this OMDL problem is really hard to compute, and I need to say if, right, because we don't know, it's just an assumption, then the scheme is secure, and the implication was wrong, not the OMDL problem. Here this is still fine. I mean, as I say, it's an assumption. We don't know if it's hard, but this was not a problem here. Yeah, the algebraic OMDL, this is maybe just a tiny variant, but it's not really worth talking about it. Maybe when we come to the models. Yeah, we need this one OMDL assumption for MuSig2 also. And we always also need the random oracle model, and the random oracle model is basically a cheat. So cryptographers are not only really bad at proving that particular things are hard, for example, OMDL, so that we need to assume them. We are also pretty bad in arguing about hash functions. So modeling hash functions without special tricks is possible, but it's very, very restricted, and we can't really prove a lot. So that's why at some point people had the idea to cheat a little bit and assume that the hash function behaves like a random oracle. So what's a random oracle? Oracle is basically a theory word for an API. So the magic API, you can just ask it something, you send it a query, and you get a response back. And here we model this, when we say we model a hash function as a random oracle, that means that when doing a security proof, we assume that the hash function behaves like such an oracle where the reply is totally random. So you send it some bit string x as input, and you get a totally random response. And of course, it's a function. If you send the same bit string x twice, you get the same response back. But otherwise, if you send a different one, you get a totally new random response. And if you think about the practical hash functions, that is SHA-256, that's kind of, there's some truth in it, right? Because you put some string in there and you get a kind of random looking response. But modeling this as an oracle is really an entirely different beast in a sense, because it basically says that the attacker can't run this on their own. Usually a hash function, I mean, normal hash functions in the real world, they are algorithms, right? They have code, you can run them, you can inspect the code, you can inspect the computation while it's running, middle states, and all that stuff. Whereas an oracle is some magic thing you send a message to and you get a magic reply back, and you can't really see what's going on in the middle, for example. And this is something where we restrict the attacker, where we force the attacker to call this oracle. And this makes our life in the proofs much easier. Now you can say, okay, this is cheating, and in some sense is, but it has turned out that in practice it works pretty well. And we haven't seen a real world example where this causes trouble. So that's why this methodology is accepted, at least for applied cryptography, I would say.
I have a question about that.
Yeah.
Yeah, I noticed that I think in BIP 340 and also in MuSig, there's been talk about using variable length for the message as a parameter. Now, does that variable length play into this random oracle model assumption, or is that completely separate?
I think it's rather separate, right? Because I think it's separate. It's, of course, I mean, if you have longer messages and you need to hash the messages at some point, so they will go as an input to the hash function, and then depending on how you model that hash function, that will be an algorithm then, or a magic random oracle. But I think the question of how long the message is kind of orthogonal to how you model the hash function then.
Okay, thank you.
I think one maybe interesting example is, or to give you an idea how this helps in the proofs is, it helps at several points, but one easy example is that we can force the attacker to show us to show his input. So when we do a security proof, what does it look like? I said the theorem is something like, okay, if OMDL is difficult to compute and we model a hash function as a random oracle, then MuSig2 is secure, roughly like this. And how do we do this? We prove by contradiction. So we assume that there is a way to attack MuSig2. So there is a concrete attacker algorithm that breaks MuSig2. And then we try to use that algorithm to break OMDL. And then because if we actually assume OMDL is not breakable, then this is a contradiction. So the attack against MuSig in the first place can't exist. So this is this proof by contradiction methodology that we call reductions. And random oracle model, for example, helps us to see what how the attacker algorithm that we are given in this proof by contradiction uses the hash function. Because if we just were using SHA-256 as an algorithm, then this attacker algorithm can use the SHA-256 internally, and we can't really see what's going on. But if we don't give it the SHA-256 algorithm, but we force the attacker to call this random oracle, to call this magic thing, then we see the calls. So we see all the inputs that the attacker algorithm gives to the hash function. And then we can play around with them because we see them. We can make use of that knowledge that we get. But if you think about it, it doesn't model the real world, right? If there is some attacker somewhere in the world trying to attack MuSig2, it's not as friendly and sends us over all its inputs to hash functions, right? It just doesn't happen. That's why this model is kind of cheating. But as I said, it turned out to be pretty successful. maybe Elizabeth, do you want to add something?
Yeah.
Because whenever I try to explain these things, I gloss over so many details.
Yeah, I think we use this notion of kind of this idealized something, right? So in the case of random oracle model, we're saying, a hash function should output something random. So we're going to pretend that it's like a truly random function. But yeah, I think like what that means is that when we idealize the hash function in that way, it says that if you are going to break MuSig, you have to do something really clever with the explicit hash function that's instantiated. So your proof of security says the only way you're going to break this scheme is if you do something clever with the hash. So it kind of eliminates all other attack vectors and just creates that one. And so far, nobody's been able to do anything clever with the hash, but it just eliminates basically every other weakness except for that, which is the explicit instantiation that's used. That's my 2 cents anyway.
Right, that's a good way to say it. It's really like you, when you think about the theorem again, it's like if OMDL holds, this is the one thing we need to assume, and if we model the hash function as a random oracle, then the scheme is secure, which basically gives you a recipe to break MuSig2 in a sense. Either you try to break OMDL or you try to break the hash function. These are the 2 ways, and as long as those things hold up, can be sure that that MuSig2 is secure. Yeah. And then you also asked about the AGM, the algebraic group model, and this is another idealized model. And here we are not talking about the hash function, but we're talking about the group arithmetic. So all this discrete logarithm stuff takes place in a algebraic group. This is okay. This is now very confusing when I use this terminology. I mean, when I say algebraic group, I just mean a group in algebra terminology. So a mathematical object. But when cryptographers say algebraic, they mean something different. Here we restrict the attacker in some more way. So we kind of say the only way to compute in this group is really to add elements. So in a sense, if you have a public key A and you have a public key B, the only thing you can do with this is compute A plus B, or maybe A minus B, or A plus 2B, or something like this. But you can't really, for example, you can't come up with your own public key except drawing a new X and computing G to the X. You can also do this. But except, yeah, you can do this point addition. So you can add public keys and you can generate new public keys by drawing the exponent and then raising G, the generator, to the exponent. But this is the only way. We assume that this is the only way you can come up with group elements. And this is again then very helpful in the proof, because it basically boils down to the attacker. So when I talked about the random oracle, I said the attacker needs to show us the inputs to the hash function. And here in the algebraic group model, the attacker needs to show us how it came up with group elements. For example, what could happen what could happen is that we send the attacker a public key G to the X and ask it to produce a signature on this public key that we haven't created before. That would be a break of MuSig2. And now the attacker could say, okay, here's a signature, and signature will contain a group element, and then the attacker needs to tell us how it computed this element. This is an implication from what I said earlier. So if you assume that the only thing the attacker can do is add those things up, then this basically is equivalent to forcing the attacker to tell us how it came up with these elements and give us the numbers basically. And this again helps in the security proof.
But there isn't a yeah, sorry, go for it.
Yeah, and it mostly has theory implications only. I would say as long as this model really holds up. And it was kind of, I think, a special thing even in MuSig2 that we had two variants of the thing, where the variant with the algebraic group model where we need the stronger assumption in a sense is a little bit more efficient.
There isn't a strictly increasing, like neat, strictly increasing levels of security, right? It's just different paradigms, because the algebraic one more discrete logarithm is weaker security than one more discrete logarithm. But how does one more discrete logarithm compare to AGM and ROM?
Okay, well, maybe let me try to explain it the other way around. So far we have talked about assumptions and models, right? And they're a little bit similar. So also the random oracle model in some sense is an assumption. Whenever we add an assumption, our proofs get weaker because we need to assume more. So for the basic version of MuSig2 for the security, we need to assume that OMDL is hard, and we need to assume the random oracle model. If we on top assume the algebraic group model, then our security proof gets weaker. That means that now there's an additional thing that can break down. So if this algebraic group model thing, which is another cheating thing, if this doesn't hold up in practice, then scheme might be insecure. On the other hand, what we get out of the security proof is that we now can have a more efficient way to do MuSig2. And the algebraic one more DL thing is really a slight variation of OMDL, and this is very confusing, even in the paper, I think sometimes. So you could have, I mean, maybe this was your impression now. Basically, if we add this algebraic assumption, then this becomes weaker. So we have a stronger assumption, so our results become weaker. And for the assumption, it's kind of the other way around. But this is really, I'm not sure how to. I mean, I could explain it, but I'm not sure if anyone will understand if I try to explain this in a minute now.
Okay, we'll move on because it's not going to be. We're not going to do a whole session just on the difference on the security proofs.
And if you're really interested in the paper, I hope we explain it. But of course, it's written with a specific audience in mind.
I've just heard this is weaker, this is stronger. We got a stronger proof, we got a weaker proof, and I'm just struggling to monitor which one you're going from one to the other.
And it's hard because you say weaker proof and stronger assumption and so on, and then you
I was going to say
even we get confused. Yeah.
The term weaker and stronger actually means different things in different contexts. So a weaker assumption means better.
Right.
A stronger assumption is worse, but then like you get stronger security, or I think there's actually a point of confusion just in terms of the terminology that we're using.
And it even confuses cryptographers. I mean, that's why we had to. So when you look at algebraic OMDL, it's a weaker assumption than OMDL. It's slightly weaker, maybe, which is slightly better. So we have to assume less, which gives us a stronger result. And but even I think cryptographers are trained to believe that whenever they hear the word algebraic, it's something bad, because now we have to make all these assumptions. But in this specific case, we're actually making a weaker assumption. That's why we stressed it so much in the paper. That I think whenever we say algebraic OMDL, we have we have a relative clause that says it's actually weaker than OMDL, just to remind the reader that what we're doing is actually a good thing and not a bad thing. Yeah.
Okay, let's move on because otherwise we'll be stuck on this all time. But thank you for those explanations.
Yeah.
I'll look at the papers again and hopefully I'll understand it a bit better. Okay, so what we were doing history. So let's get back to the history. So we had MuSig. We went through broken MuSig1. We went through corrected non-broken MuSig1. Then there was MuSig-DN. And this hasn't been
right.
Yeah, sorry.
This was DN was even before the MuSig2. Right?
Right. Yeah. So we haven't gotten to MuSig2 yet. But MuSig-DN hasn't been that hasn't been implemented. Like, there's no one working on that, right? It was just like it was an advancement in terms of like academic research. But like there's no use case that you've seen so far for why people would use MuSig-DN.
Yeah, maybe there are some use cases, but it's much more difficult because I mean, from a practical point of view, what does it do? It so multi-signatures have some specific risks when using them in practice, at least all these schemes we're talking about here. So for example, you need secure random numbers while signing. If you have broken random number generators, and this has happened in the past, not in the context of multi-signatures, but in other contexts, then you might lose security entirely. So basically you try to sign a message and the others can extract your entire secret key, which is a catastrophic failure. And MuSig-DN is an attempt to get rid of this requirement to have real randomness, which sounds good in practice, right? Because it removes one way things can go wrong in practice. But on the other hand, the way we're doing this is that we add a huge zero knowledge proof to the protocol, which again comes with a lot of engineering. First of all, we lose a lot of efficiency, but even if you ignore this, it comes with a lot of engineering complexity. And all this engineering complexity again could mean that something could be wrong there. So in a sense, we're removing one foot gun and maybe we're adding another one. And adding that other one is a lot of work to implement. So I think that's why it hasn't really been used in practice so far. I still believe that there are niche use cases where it's useful, and there have also been other papers, at least one other paper that actually does a very similar thing to what MuSig2, what MuSig-DN does, but in a more efficient way. So their method is more efficient than ours, but it's still very complex. It doesn't use zero knowledge proofs. It's complex in a totally other way, but it's again a lot of engineering complexity. So it seems that there is no simple solution to get rid of this randomness requirement.
Right. So MuSig-DN is actually better both for the randomness requirements and stateless signing, right? It's just that those benefits aren't obvious in terms of why someone would really want those benefits.
Yeah,
for a particular use case.
Right. So yeah, first of all, so the randomness and the statelessness they're very related. If you look at the details, so if we remove, so the scheme the MuSig-DN has 2 rounds, and when I say it's stateless, it basically means that when I send the one round is to send a message, then I receive messages from the others, and then I send another message. That's why it's 2 rounds. And when I say it has state, then the signer needs to remember secret state from from the first round to the second round. And this can be problematic because weird things could happen while you remember state. For example, you could run in a VM and maybe someone you do the second round and then someone rewinds the VM, resets the VM to the point where you did the first round but not the second round, and you still have the state. And you get you do another second round and then you lost again. And the basic idea is that if we remove the requirement to have randomness, then everything will be deterministic. So that's why we don't have to remember state, because when we come to the second round, we could just recompute the first round again, because it's deterministic. So we just, at the moment we're doing the second round, we can do we can redo the first round again. So we don't need to remember it because there's no randomness involved. That's why having no state and requiring no randomness are pretty related in the end. And I think the real motivation would be really to because we have seen random number generators fail in practice, and even in Bitcoin, and people lost their coins due to this. So it's a real problem. But for multi-signatures, we currently just don't have a good way to avoid the randomness requirement. So maybe from an engineering point of view, it could make more sense just to focus on really getting the randomness right instead of trying to work around it. Yeah.
Okay. Do you want to add anything to MuSig2, Elizabeth? Did you ever look at MuSig2?
No, I would just say that I think there are some niche use cases for having a deterministic nonce, like if this gets used in combination with something else. Like I personally kind of have thought about a few things that use it, so I wouldn't just say, like I think it's actually a really nice result, even with the expensive zero knowledge proofs, but like maybe there's something that could be done there, I don't know. But I think that it's not just like pushing, the problem to somewhere else. It's actually like a different construction, and I do think that determinism is kind of useful when plugged into like other schemes. So I still think it's something worth pursuing, and I like this result.
Okay. Yeah, we thought about using the core of it in other protocols and problems, but we haven't really found anything.
Okay. Okay, so then MuSig2. So this is getting back to 2 rounds, right? This is exchanging nonce commitments in advance to remove the 3rd round of communication, right?
Right. So yeah, MuSig1 again had so the fixed version of MuSig1 had 3 rounds. They needed to introduce this pre-commitment round before the other 2 rounds to fix the problem in the security proof, or to actually make the attack go away. I mean, it wasn't just a problem in the proof, it was really that the scheme was insecure, as we discussed. And then MuSig2 kind of found the right trick to remove that first round again. And whenever I say this, I should mention that Chelsea Comlow and Ian Goldberg found the same trick parallel to us for Frost. Basically, it's really just the same idea, just in a different setting.
Mm-hmm.
Or actually, even Ibra and Burgess was the 3rd team that found the same trick in parallel. So it was really interesting to see three teams independently work on the same problem. So apparently, it was really a hot problem.
And this is strictly better than fixed MuSig1 and MuSig2. Well, no, MuSig2 did still have some advantages, right? It's just that for most use cases,
yeah, I think
we
in this blog
expect
post,
MuSig2 to be the best MuSig.
Yeah. So in this blog post, we argue that MuSig2 is strictly better than MuSig1, because has the same safety requirements. It just gets rid of one round. And you can pre-compute the first round without having a message, which is another big advantage. This basically means you don't need. So what you can do is you maybe, for example, in a 2 of 2 Lightning channel, that in the future maybe using MuSig2. What you can do is you can do the first round already before you know what to sign, and then when a message arrives that you want to sign, so that is a payment and Lightning payment that you want to forward or you want to do. Only then you can do the second round. And because you already did the first round, the second round basically is just one more message. So that arrives at one point of in particular, it's in particular useful for really these 2 of 2 things, where because then the transaction arrives at one endpoint of the Lightning channel. This endpoint can complete the second round of MuSig2 for that particular transaction. So compute something locally and then just send it over to the other endpoint, and the other endpoint will do its part of the second round, and then already the other point at this point already has the full signature. So then it's in a sense it's really just one message that goes over the network. So that's why you could call this semi-interactive or half interactive or something like this, because in a sense it's still interactive because you have 2 rounds, but you can always pre-compute this first round, and then whenever you really want to sign a message, then it's just one more message over the network. That's why we believe MuSig2 is strictly better than MuSig1 in practice. But as compared to MuSig2, it's really hard to compare, because MuSig2 has this additional feature that it doesn't need randomness, and if you do the zero knowledge proof correctly and implement all of this correctly, you definitively remove that footgun of needing randomness. So this is a safety advantage in a sense, but on the other hand, it's slower, it has more implementation complexity, and you can't do this pre-computation trick, so it's always 2 rounds. You can't pre-compute the first round. So these would be at least 3 drawbacks. But as I said, it has this safety improvement, so it's kind of, you can't say that one is strictly better than the other. But I think in practice, what people usually want is MuSig2, because it's simpler.
Right.
And we like simple protocols, not only because they're easier to implement, but they're also mainly easier to implement correctly. And crypto is hard to implement, so whenever we have a simple protocol, we have much less potential to screw it up.
And on the security proofs, you've proved the security of MuSig2 in the random oracle model. Let's read up. A security of a more efficient variant in a combination of the random oracle and our direct group model. Yeah, I don't know. Maybe I'll never understand that. Both our proofs rely on a weaker variant of the long loss. Okay. Okay. MuSig2. Any other comments on MuSig2, Elizabeth?
No.
We'll actually we'll get on to speedy MuSig.
Yeah.
That's an additional MuSig protocol.
Yeah.
Okay, let's do that now, actually. So this is your this is your paper with Chelsea Conlon and Mary Muller on, and this has a speedy MuSig2 in it.
Yes.
And it is using proofs of possession, which MuSig2, well, none of MuSig1, MuSig2, and MuSig2 use proof of possession, I think. And this uses proof of possession. And you argue in the paper that this could potentially be better in certain examples or use cases.
Yeah, so basically, MuSig2 has this really nice key aggregation technique. But what we do instead is we include proofs of possession of your keys. So we talked about a little bit before about how you want to avoid these rogue key attacks. So one way is if you prove knowledge of your secret key, then you can't do that kind of attack. And so if you do that, then the aggregate key for all the parties signing is just the multiplication of their individual keys. So that makes like a more efficient scheme. And I would say like a use case where this might work really well is if you're reusing a key. So it's a little bit more expensive to produce your key in the first place because you are computing this proof of possession. But if you're reusing keys a lot to sign, then that might be, it's an alternative.
Right. And is this where Bitcoin has very specific requirements which make MuSig2 better than using proofs of possession like a speedy MuSig type scheme? I think in the MuSig2 paper it says proofs of possession makes key management cumbersome in a Bitcoin environment, complicates implementations, not compatible with serialization formats. This is like Bitcoin specific stuff, right? Is it like BIP32 keys and things like this, or what is this that makes MuSig2 better than speedy MuSig in a Bitcoin environment?
Yeah, I'm not sure if it's really better is even the right word. I think it's just another trade-off. It makes, I think, so the proofs of possession are pieces of data that you need to add to the public keys. So this means that when you want to aggregate a few public keys, you need this additional piece of data. Now that's kind of data that we didn't have in so far in the public key. So and then we wouldn't have it on blockchain. So for example, if you have if you're having if you do some crazy protocol where you take some random public keys from the chain, or you take specific public keys from the chain without any additional context, and you aggregate them, then certainly MuSig2 is better, because then you just wouldn't have access to the proofs of possession, and you would need to ask the other signers to send the proofs of possession first before you can aggregate the key. On the other hand, you can say, okay, in practice, we usually anyway talk to the people that we want to have multi-sigs with, so they could send us their proofs of possession when we ask them.
Right, and I guess the idea is
I think
like
both is true in a sense.
Yeah, but I guess the idea is like the key is a little bit larger, but if you're reusing the key constantly to produce these signatures, then you only have to do it once and then you can reuse it. So I guess it just depends on the use case mostly.
Yeah, I mean, speedy MuSig, I mean, the name already says it, right? It's a little bit more speedy.
Just faster, yeah.
It's faster, and then MuSig2 is maybe a little bit more convenient depending on your use case. And this is the trade-off. But it's, in the end, I think it's a not a big deal. You could use either. For most applications, at least.
I was thinking this was like maybe this is completely off topic, but I thought this was like Bitcoin using BIP32 keys and having specific requirements there, meaning that it would want to use MuSig2 over speedy MuSig. But that's veering off course, right? The 32 is a separate issue.
Yes and no. I mean, BIP32, it maybe depends on which particular way of derivation you use here. I mean, BIP32 for the others is a way to derive multiple public keys, a lot of public keys from single key material, from a single secret key in a sense. And if you use there are two ways of using BIP32. There's public derivation and hardened derivation, I think. In the hardened derivation, this is what people mostly do. There's just a signer with a secret key, and this guy creates all the public keys and sends it to other people. And in that model, it doesn't really make a lot of difference, because the signer anyway has to generate a public key and send it to someone else, and then it could just attach this piece of data, which is the proof of possession. If you do public derivation, which is a little bit more advanced, where you as a signer give in a sense a master public key to other people, and they can derive more public keys that belong to you, that would be harder because they can't derive the proofs of possession. Now maybe they wouldn't even need to. I never thought about this. Now that I say this, maybe this would work. You should think about this. To be honest.
Yeah, I think we should chat more about this actually. Like,
I think it would work because yeah, you're just streaking the key. Yeah.
I should say that
okay.
the proof of possession is, in our case, it adds like a couple of elements. So it's like it's a Schnorr signature on your.
It's really just a Schnorr signature.
Yeah. Yeah.
It's so confusing because we say proof of possession, but it's actually again it's just a Schnorr signature.
It's another Schnorr signature because we love them so much. Yeah. Right. So I mean, you're basically just adding one group element and one field element exactly as a Schnorr signature to your public key.
So, I mean, the Bitcoin specific things, sorry, there's some noise outside. The Bitcoin specific things are, as you're saying, you're describing like the hierarchical deterministic key generation, like a tree of keys that we have in Bitcoin. I don't know if they use it in other blockchains, other cryptocurrencies. Yeah, hardened and unhardened derivation. But this is, as you said, this is generating lots of keys from a root key. And we have a thing in Bitcoin where it's like, we don't want to reuse public keys or addresses. We want to like keep rotating them. So perhaps that Bitcoin requirement or like expectation that you only use your public key once for a single transaction and then rotates to like a new key generated from that tree impacts whether you'd want to use MuSig2 or Speedy MuSig.
Yeah, I think it's hard to say. I think there's nothing specific about the way we use keys in Bitcoin that would mean you can only use MuSig2 and not Speedy MuSig, or which would mean you can't use proofs of possession. It's just it makes key management a little bit easier and also more backwards compatible to what we already have in our implementations. But it's really not, I think, not a fundamental thing. So I think everything you could do with MuSig2, or almost everything you could do with MuSig2, you could also do with Speedy MuSig.
Okay.
I think maybe you should ask Peter about this because he has stronger opinions. I always argue that proofs of possessions are not that bad, and Peter said, but let's avoid them. Okay, but yeah, I think it's not really a fundamental difference.
I saw a presentation from Andrew Polster who said apparently Ethereum has public key recovery from the signature, and someone asked about this, and he said that is not a good idea because of BIP32 keys in Bitcoin, and that you need to commit to the public key.
That's interesting.
And he was quite strong on not wanting to enable that. Apparently, there's a covenant proposal that comes out that if you can do public key recovery,
okay, yeah.
And Andrew was strong on saying that we shouldn't enable that because of BIP32 keys, which is kind of assuming BIP32 keys are fundamental to how we use Bitcoin or how we use Bitcoin in real life.
Okay, I don't know what he had in mind there. I mean, I don't know this proposal, but at the moment I can't think of a way how BIP32 would interact with recovery. I don't know. Not sure what he had in mind.
That's a question from Andrew, I think. Okay, anything else on Speedy MuSig? Any questions from the audience? Comments on YouTube. I've got one saying Belar never needed all keys for verifying. Maybe.
Yeah, right. I think we covered that. Yeah.
Yeah. Okay, so let's go further down MuSig2. So MuSig2 now has a draft bit.
Yeah, just updated it yesterday.
So
still work in progress.
Yeah. So can you talk a bit about what work still needs to be done? Why is it still a work in progress? If it's going to be changed to be speedy music, then that would be a significant change.
That
But
would be
like, yeah,
significant change.
what other things that could potentially change in this bit?
Maybe go to the issue list, because then we have
Oh, the issue list in the Vix repo, you mean?
in the repo here. In exactly this, no, yeah, in exactly this repo here.
In Jonas Nick's fork or the actual repo?
Yeah, and in the fork.
Oh, Jonas Nick's fork. Okay, sorry.
So I think it's mostly, or just 11 minutes ago, someone opened the issue, so that's new. I can't talk about. Yeah, okay, that's just writing. So I think we, if I have a look at this list now, we merged a few PRs yesterday. Most of the things I think in the actual algorithms are pretty stable. Can you go back to the open list? So I think almost all of what I see here is either already worked on or is really just improving the writing and the presentation, but not the actual algorithms. One very interesting point here maybe is issue 32, the principle of just-in-time X only, which is maybe something I forgot to mention when I talked about X only keys. Here Lloyd argues that we should use X only keys in a maybe different way that reduces some of the pain that I mentioned earlier. I mean, I said like X only keys save 1 byte on the blockchain in the public key, but they introduce a lot of pain in the algorithms. And Lloyd here has a proposal to just maybe a different way to think about it, and which reduces some pain. And this is a really long discussion, and I think we at least agreed on making certain specific changes to the BIP. I think we haven't reached a conclusion on our fundamental philosophical views on how X only keys should be thought about, but at least we made progress there. And I also promised, it's a good way to remind me, I promised to write a document that explains how people and maybe protocol designers and implementers and other people should think about X only keys. So when they should use X only keys and when they should use the keys that we used earlier.
So it's actually, the X only thing is like subtly complicating MuSig2 as well. I didn't understand that. Okay.
Yeah.
I thought it was just the TLOF proposal.
No, this is what I mentioned earlier.
Okay.
It makes MuSig2, for example, more complicated, and on one side you can say it's not that bad, because anyway, I mean, we can handle this complexity in the BIP, and then we have library where it's implemented, and this handles all the complexity, but still it's complexity, yeah. And but this discussion here more turned into a discussion how people should think about X only keys, because when we released BIP 340 and then now it's even activated on Taproot, I think some people got the impression that this is the new shiny key format that everybody should use, and this is maybe the wrong way to think about it. It saves a byte, but it saves this byte at losing really a bit of information, so it's a little less powerful. And maybe a better way to think about it is that if you know that with a specific public key you really only want to do signatures, then it's okay to have it X only. But if you may want to do other stuff with the public key, maybe add it to other keys, do MuSig key aggregation, do some other more advanced crypto, then it might be better to stick to the old format. Or because old is even the wrong word. We propose the word plain now, because when I say old, it already has this. Maybe it comes with this flavor of old and legacy and bad. It's actually not the case. It's just a different format, and it really makes sense on the blockchain because there we save space. But for example, if you send public keys over the network without needing to store them on the blockchain, it might just be better to use the plain format, which is 33 bytes, 1 byte more, because you can just do more with these keys. They have one bit more information, so you they are more powerful in a sense. And I think some people and I can totally understand if you read BIP 340, you can understand that this is kind of the new thing that everyone should migrate to. In particular, also because 32 is just a number that implementers for some reason like more than 33. It's power of 2. I mean, it doesn't make a lot of difference, but it looks nicer. But yeah, maybe that's the wrong way to think about it, and that's why we had this issue. And I volunteered to write a document, maybe a blog post, or maybe an informal BIP even, informational BIP even, that explains how people or should think about these keys and how they should be used in practice, at least according to my opinion. Then that's another place where X-only keys just made the world a little bit more complex, because yeah, I mean, you could say just because they exist, right? Because now there are 2 formats and people have to choose, and yeah.
So yeah, it's quite serious then. So we'll probably be cursing that X-only choice. I mean, it's just, as I was saying earlier, it's just impossible to predict how the future goes, right? Like you have to converge on a proposal at some point. You can't just keep putting off, and because no one will work on anything because they just think, oh, it'll never actually go on chain.
I mean, we had a lot of eyes on it. Of course, in hindsight, you could say, okay, if we had written the MuSig2 BIP and the code back then, we would have maybe noticed that this introduces a lot of complexity. But yeah, it's hard to say. When at some point you need to decide and say, okay, we are confident enough. A lot of clever people had a look at this and they agreed it's a good thing, and well, and it still may even be a good thing, right? It's not really clear. It saves space. Maybe if people use it in the right way, it will be good in the end. Yeah.
So we've got another comment on YouTube. We've got pub key recovery in pre-taproot because we've got ECDSA. Yeah, I think Ethereum is still using ECDSA. So that's why it has pub key recovery from the signature. In terms
we
of
we can't do it in Schnorr, by the way. At least not with 340. Yeah.
Right. So that's like the keys that we're using, key gen. Is the other parts of the MuSig2 protocol kind of set in stone? Key aggregation, tweak, nonce generation. This stuff's likely to stay. This is going to be solidified, right?
Right. It's pretty much set in stone by now. I mean, if anybody here is really working on an implementation, when I say set in stone, don't count on it. I mean, it's still experimental, and we could change things, and this may lead to weird consequences if you use it now in production and then switch to a new version and so on. But if you ask me, yeah, I think the algorithms are pretty much set in stone, and unless someone else finds a problem. I think one thing that it's not set in stone when it comes to the real algorithms is exactly one thing that was discussed in this X-only issue there, where we want to change the key aggregation slightly. But yeah, we still need to do this.
Okay.
And we should really hurry up now. Not hurry, but I think it was there for a while now, and we should just try to get it finished.
What do you mean the bit? You mean
The bit,
hurry up and finalize the bit? Yeah.
Yeah. Because people really want to use it. We
right. Yeah.
In particular, the Lightning people approach us pretty often. You should get it.
In terms of things that can go wrong in a MuSig protocol, I mean, you do need signatures from all parties. So if like one party is not responsive, then you can't produce a signature. So you'd need like a backout, like an alternative script path. I'm guessing.
Right, but this is kind of This is true in every multi-sig thing, right? I mean, if the other person doesn't want to, or it's offline, there's no chance.
And so that's just like not either unresponsive or providing invalid signature. Like it just can't complete. In terms of like sorting pub keys, signatures, does that present a complication? I mean, if people are receiving pub keys and signatures in different orders, do you need to like allocate I think in PSBT lingo it's like finalizer. I think Elizabeth talks about combiner in the frost setting. But how do you need to fall back on that, or do you need to allocate a combiner or finalizer at the start?
So for key aggregation, the way the BIP is written, you can do both. So basically, the key aggregation algorithm in the BIP gets a ordered list, and as a data structure. So you can pass it an arbitrary list, which means you can sort the list before you pass it, list of public keys, or you cannot choose to sort it. We took this approach because it's the most flexible, and different callers may have different requirements. For example, if you use multi-signatures with your hardware wallets at home, you probably don't want to have the complexity and just sort the keys. But maybe some applications have already have a canonical order of keys. For example, in Lightning, you have a I'm not sure how they do it. I'm just making this up, but maybe there you have one party that initiates the channel and the other party which is a responder in the channel. So then you could say, okay, let's put the initiator always at position 0 or it's position 1 and the responder always to position 2. We also, I think we described this in the BIP in the text somewhere. So if you don't want to care about the order, you're free to sort the public keys before you pass them to key generation. If you care about the order, you can pass in whatever you want. Thing is just if you pass two lists or two different versions of a list in a different ordering, then the resulting key will be different. That's how it is, because we don't sort internally. And then if you're asking about, signatures. For signatures, it doesn't matter in which order you get them. This is really handled in the protocol. That doesn't matter. And but if you're asking for things that can go wrong, I think the main thing that can go wrong is what we already talked about, is the requirement to have good randomness. This is really the one thing where you need to be. It's hard to say, but you need to be careful as a implementer. Of course, you always need to be careful, and it's you need some good source of randomness, which is typically the random number generator in your operating system.
And this is a new requirement, because before with just single signatures, using the hash of various inputs to get that randomness, right? And now you do actually need a independent source of randomness.
Yeah, right. Yeah, that's exactly the thing that MuSig2 solves in a sense, but by adding a lot of complexity. And this is also a very, very nice or a very, very important thing to know. People have tried to use this trick with a hash, generating the nonce by hashing the secret key in the message, also for for multi-key, for multi-signatures, don't do this. I mean, if this would be possible, we would have added it to the to the pip, but it's totally insecure. It's really very interesting, because for years we told people when they implement signatures they should generate the nonce deterministically, because this is way safer. And this is true for ordinary single signer signatures, but funnily it's the exact opposite for multi-signatures. And this is kind of really dangerous, because I mean we've seen people do this just because we told them for years, okay, derive nonces deterministically, and then they saw the multi-signature proposal and said, okay, it's safer to derive nonces deterministically. No, just no, it's the other way around. It's strange, but that's how it is. Here, when you look at nonce generation here, it has this important note. Nonce gen must have access to high quality random generator to draw an unbiased, uniformly random value rand. Here, we even say it explicitly, must not derive deterministically. Yeah. Okay.
And so this is this going to be the biggest challenge, assuming, I mean, everything seems to take years these days, but like assuming we get hardware signer support for MuSig, the hardware wallet would need to provide this randomness, and none of them currently do, right?
Well, I mean, it's hard to say.
I suppose
anyway, you need randomness for doing crypto at all, right?
Right.
You need also randomness to generate your seed. Now, okay, in the hardware wallet case, you could say, okay, let's throw some physical dice. Yeah, but for normal computers, I think you anyway assume that you have some way to generate real randomness. But I mean, as I said, we have cases where this broke down, and we've seen cases in practice where this broke down and people lost their coins. So this is one risk. Another risk is that you have this statefulness. So if you do this trick that you pre-compute the first round in particular, which is what they want to do probably in the Lightning channel, then you also have to make sure that you can't really reuse that state twice. So whenever you have state, you have some risk in practice that you get the state of your machine gets reset to that state. For example, if you run in a VM, or for example, if you would try to backup. So let's say you do the first round of MuSig1, and then you have to keep the secret state in order to perform the second round once you have a message. And now it would be a very bad idea to write that state to disk, or even write it down to a backup, because then what could happen is that you complete the second round by sending out signatures, and then at some point the user will restore the backup, and then you have the risk that you perform the second round again, now with different inputs. And this is exactly what we want to avoid, because then you expose your secret key. So that's why we also describe it. We also say in the BIP that you shouldn't serialize the state, because even in our implementation, we don't give the user a way to serialize the state, because this could mean that some user will write it to some backup or store it somewhere else or whatever. If you really crash after the first round, no big deal. Just do the first round again. That's totally fine. And this is probably what Lightning will do. If a node crashes, well, then they anyway have to re-establish a connection to the other Lightning node, and then they can just run the first round of MuSig again.
You can tell me to mind my own business. Have you had any discussions with hardware wallet devs? So you've got a hardware wallet at Blockstream. Any discussions with those guys? Like, how long would it take? obviously the bit has to be finalized. You probably want a lot of experimentation before you
Actually,
make that investment. But yeah,
it's a good question. We should talk to hardware wallet people more. So far, we mostly were in touch with Lightning people because I have the impression they really want to use it, so they talk about it very very often. And
certainly,
I think in Lightning I don't know why, because I don't know the specifics I don't know the details of the Lightning protocol, but I think in Lightning they said the statefulness is okay, because anyway, if you lose state, and it makes a lot of sense in Lightning now that I think about it. If you lose state and you crash, you anyway need to trust the other side, that they won't steal your entire channel. So for them, they say it's not a big deal that they have. I mean, they already have this assumption in their threat model, so the additional state introduced by MuSig2 doesn't change it really.
Yeah, I think I've got a few links. I think it's specifically like the Lightning Labs, L&D devs, like Lally, etc. Really keen to. I think they're already. I don't know if they're already using it. Loop is actually one of their products. Maybe I've incorrectly said MuSig2 is being used.
Not sure if it's. I hope. I mean, I wouldn't say I hope. Of course, I hope my stuff is used in production, but at least they need to be careful if now we update the pip and do some small changes. They have to be careful that it doesn't break, because at the moment we don't care too much about backwards compatibility, right? It's not 0.1 at the moment. It's not even a pip, right? It's a pip draft, so yeah.
Yeah, merged is concerning, but perhaps it's just an option and they're not actually using it in production. And it's support for MuSig2 as well. Okay. I guess I don't want to cover Lipstick P before we finish. But we do have Elizabeth here, so we should talk about Frost. Okay, so Frost. I have a quote from you, Tim. I'll read it out. It was a couple of years ago, but if you still believe you still have this view. It should be possible to marry MuSig2 and Frost papers together and get a T of N with our provable guarantees and our key aggregation method. You still share that view now? Or, I mean, my understanding of Frost is that there's a lot more complexity, there's a lot more design choices.
Sorry, could you just repeat what you said? It was hard to hear when you turned around.
You want me to say your quote again, or my question?
The quote, yeah, I couldn't.
The quote, okay. It should be possible to marry MuSig2 and Frost papers together and get a T of N with our provable guarantees and our key aggregation method.
Yeah, I believe it's still true. But
okay,
it's only a belief. I mean, I'm not sure what Elizabeth thinks, but I think it's possible to create a scheme where you have a tree of key aggregations where some of those would be MuSig, some of those would be Frost, so some of those would be multisig, some of those would be threshold aggregations. It's just very hard, I think, to formalize and prove secure, because then you get all the complexity from all the different schemes.
Yeah, I think it's worth pointing out that because Frost is a threshold signature scheme, there's a lot of added complexity with the key generation. So when you have a multi-sig, basically you have a nice compact representation of the key representing the group. But as soon as you move to the threshold setting, now you need some kind of distributed key generation, which often has multiple rounds. So there's a trade-off there in terms of kind of flexibility or having a nice key generation algorithm. So these are just like different aspects.
So yeah, of course you can. Yeah, sorry, go for it, Tim.
Yeah, it just maybe it's not exactly related to that point of the discussion, but I think there is, or I'm sure there is this RFC proposal for Frost. I think this wasn't included in the reading list, right?
Sorry, what? What specifically?
There is a draft RFC for Frost.
Yeah, there's so Frost is being standardized through NIST, and there's a CFRG draft which has gone through several iterations.
You
So
mean
yeah,
ITF or on his
ITF, yeah. So
yeah.
it'd probably be helpful to like pop those links into the list also.
Okay, yeah, I'll definitely do that. So yeah, it's a threshold scheme, but you can actually, obviously you can, the K of n, the K can equal n. So you can still do multi-sig with Frost. It's just a question
Sure.
of whether you would do that.
I think you wouldn't, because if K equals n, then
Yeah.
You only get the disadvantages of Frost and not the advantages.
Yeah, not the right, exactly.
A couple of things I wanted to confirm with you guys. Jesse Posner, who's writing with the Frost implementation in libsecp zkp, he said a couple of things. I just wanted to confirm that this is true. I think he was a bit unsure when he said them. So with Frost, you can swap out public keys for other public keys without having an on-chain transaction. And you could also change, say, from like I don't know, 2 of 3 to a 3 of 5. Again, without an on-chain transaction. So there's a lot of flexibility in terms of what you can do for like moving the off-chain protocol around and making changes to it without actually needing an on-chain transaction, which seems very flexible, certainly when you compare it to like MuSig2. I mean, the only way you can change the multi-sig arrangement for MuSig2 would be to have an on-chain transaction, right?
I think I'm not sure I really understand that statement, because like if you're changing keys around at all, then you need to rerun the distributed key generation protocol. So
right.
I'm not.
I'm also not sure what Jesse is talking about here. I mean, I think in the pull request there were some discussions about what you certainly can do. You can downgrade, in a sense, n of n to k of n. I think this has been discussed, but I'm not. So, for example, swapping out a key to a new key, I think maybe Elizabeth knows more. There are some key resharing schemes.
Yeah, I mean, so you
I'm not
basically
really aware of those.
Yeah, so I mean that's what I was saying about doing the distributed key generation again. So basically, say you run distributed key generation once and everybody has their secret shares of the overall group key, because at least the DKG that's used in conjunction with Frost, like the original one, which is also what we prove like in our paper, it's based on Shamir's secret sharing. So there's some like pretty standard ways to reshare using Shamir. So that is possible. But I mean, it's still like non-trivial.
And it kind of needs so you can do resharing, but it's more like a forward security thing, right? It's you can't reshare through an entirely new group of signers. You would still trust the old group of signers.
Yeah, you can transition from some group of signers to a new group of signers also. So there are ways to reshare the keys, or you can keep the same group and just kind of reshare like a sharing of 0 kind of, so that like your shares essentially kind of stay the same or same group, or you can switch the group of signers. But it does involve performing the resharing. So there's a little bit that has to be done there.
So you would need to redo the protocol, which surely means you'd need an on-chain transaction in like Bitcoin or blockchain lingo, right? It's not a case that you can have some funds stuck behind an addressed public key and keep that public key associated with funds but
Right,
like
you have to- you have to-
rejig the protocol behind that public key.
Right. When you reshare, you do have to like send some values to the other parties so that everybody kind of has their new shares. So
Yeah, and the old group would still have to sign in keys.
right.
So I mean, you can't hand over. It's like a normal Bitcoin. I mean, you can't when you so let me say it this way: when you have a normal coin with a normal UTXO and single signer, of course, what you can do is you can take your secret key and send it to another person and kind of hand over the keys. But the way this is not really secure because the other person needs to trust you because you still have the key. And this would be the same in this Frost resharing. So you can do the same transition from I don't know, from one group where you have a 2 of 3 sharing to some totally 3 different parties, which then again would have a 2 of 3, but they still would need to trust the old group not to spend the coins. So it doesn't in that sense it's doesn't give you magic way to overcome this problem. But whenever you want to hand over coins to a new person in a secure way, you need to do a transaction.
Yeah, I think it's worth pointing out too that distributed key generation is dealt with as an entire field by itself. So how to reshare things like, so when we say Frost, I mean, it kind of consists of these 2 components. There's the distributed key generation protocol and then the signing. And what we tend to kind of focus on is the signing because you could incorporate really any number of distributed key generation protocols with the Frost signing mechanism. So in terms of like properties you want out of key resharing, like this is basically within the realm of distributed key generation research, not really like Frost research.
Mm-hmm. And Frost also uses proof of possession, PEDPOP.
Yeah, so the original Frost paper proposed a distributed key generation mechanism, which is basically the Pedersen DKG. So this is like a pretty standard DKG in the literature, with the addition of proofs of possession. So that was why we proved our version of Frost together with the key generation protocol that they proposed. But it's basically just Pedersen plus proofs of possession.
So maybe one thing to mention here is that or to go maybe step back is what and to reiterate what Elizabeth said. So threshold schemes are in general more complex than multi-signature schemes because not only the signing part is interactive, but also the key generation part is interactive. Where
Right.
in the MuSig paradigm, you basically can just take some public keys and aggregate them.
Right.
And in threshold schemes, at least in those that work in the groups we have in Bitcoin, with the crypto and Bitcoin, even the key setup process is now interactive. And this is, of course, again, another layer of complexity. But one interesting side effect here is that now, if we anyway always during key generation need to talk to everybody, then we certainly can also send around proofs of possession because we anyway talk to. Anyway, there's a must requirement that we need to talk to everybody else during key generation.
Right.
And then
yeah,
sending proofs of possession around is the natural thing to do. Then there's no drawback because we have the drawback already in a sense. That's why all these proposals then use proof of possession and not MuSig key aggregation, which would probably be possible, but just lose some efficiency then.
The Bitcoin implementation of Frost uses MuSig key aggregation.
Yeah, I think it does.
Frost.
I think the motivation. So Jesse said it's easier because then it's the same format or the same method. So we could reuse some code, and it would be, for example, possible to do what he described there. So maybe you could start with a 3 of 3 setup and then downgrade it to a 2 of 3, something like this, and then it would make sense to start with the music setup, because then when you start with the n of n thing, you probably want to have the music method. But this was still I think an open point in this PR, because he came up with this use case, and then at least I wasn't really convinced that people want to do this in practice, and others maybe weren't convinced either. So we are not just, I think we haven't decided yet. So in general, this at least in the Bitcoin world, when you talk about this PR, then this is much more work in progress than MuSig2, where in MuSig2 we already have the BIP draft, and it's, as I said, it's almost finalized. And here we don't even have a specification. We just have this draft PR, which tries to implement it, but without an explicit specification now. And I think it's worth mentioning that in outside Bitcoin, it's maybe the other way around, right? Because there is this IETF proposal for Frost, and there's nothing for multi-signatures actually. So this is again maybe.
So why is that? Given that MuSig is simpler, and is it just that Elizabeth's done better speaking to the IETF than Bitcoin does?
I mean, I think there are a few things to say. First of all, yes, MuSig is simpler than Frost, because just multi-signature is simpler than threshold signatures, mostly because of the thing we just mentioned, that key generation is non-interactive in multi-signatures and interactive in threshold signatures. Now the second thing is use cases. I think in cryptocurrencies, multi-signatures have some use cases, and because in cryptocurrencies you anyway always have an escape hatch when the other parties go offline. For example, in a 2 of 2 Lightning channel, you always need to have some time lock that says, okay, if the other party disappears, then I can get the money back after some time. If the other party disappears, we can't just create a new key, right? Because there's money stored under this key, and money would be gone. That's bad. In other applications, and the IETF is probably not interested in cryptocurrencies. In other applications, threshold signatures make a lot of sense. Also in a lot of blockchain applications, but yeah, as I said, in the blockchain we have these special cases where also multi-signatures make sense. But in general, I think if you ignore cryptocurrencies for a moment, then threshold just makes more sense, because you can scale it better. I mean, it's pretty useless to have a 10 of 10. So what's the goal of all these schemes? To distribute trust. But with multi-signatures, you always kind of increase security, but you decrease safety, because two things can happen. Either some people get malicious or steal your keys. That's great with 10 of 10. I mean, 9 people can get compromised, their keys stolen, the scheme is still secure. But on the other hand, you always increase the probability that you lose the key material, right? If you have a 10 of 10 and you lose one of the 10 pieces, well, then again, the key is gone. So you increase security against attacks, but you decrease security against just losing your keys. And the only way out of this dilemma is threshold signatures, where you don't need to do a 10 of 10, but you could do a 7 of 10 or something like this. And then you can trade off this security against attackers against security against losing stuff. And this is something you can really only do with threshold keys, and I think this is why in general people are more interested in threshold things. On top of this, in Bitcoin now I mentioned something like contracts, for example, again Lightning or other complicated things, but we always have an escape hatch in those contracts. And even in other setups, for example, at home, when you store some larger amount of coins, maybe you want to have a 2 of 3 between 3 hardware wallets or 2 hardware wallets and your machine or something like this. This is a setup that I think a lot of people use. And even there you want already threshold, because again, if you lose one hardware wallet, you don't want to lose all your coins. But there are some using Taproot. There are some ways you could do this even with multi-signatures. For example, you could have a Taproot output that's a 2 of 2. So yeah, let me explain the setup. Say you have 3 signers, 2 hardware wallets, 2 hardware wallets and a backup wallet somewhere else. Now you could have a Taproot output that's just a 2 of 2 of the 2 main signing wallets, and you have some script paths that cover the other possibilities. So that is, you have 2 primary devices, and as long as you have access to those, you just use this normal key span. And whenever you need to resort to the backup device, okay, then you need to open the Taproot commitment and show the script path and so on, and then use the other MuSig combinations. But you could basically implement this 2 of 3 via 3 combinations of 2 of 2s. And in the end, this may be more convenient in practice than going through the hassle of running this interactive distributed key generation that you would need for Frost. And people are also thinking about this. And I think this is another reason why multi-signatures are interesting in Bitcoin. But of course, I mean, this doesn't scale. I mean, if you want to do, I don't know, 20 of 60 or something like this, or 20 of 40, you probably don't want to do this at home, but yeah, you can't enumerate all the possibilities. This would be very inefficient.
I guess like finalizing the bit, it's a bit closer to the use case than an ITF standard, right? The ITF standard would just be like we have this paper, academics are happy with the proof, but it's not speccing it for a particular real world use case. Would that be correct in saying?
I think it's speccing it, right? I mean, it's a specification, but maybe Elizabeth knows more about the use cases that they have in mind, or that you have in mind.
I don't know, Elizabeth, are there particular use cases that this like ITF standard is being geared towards, or is this, I mean, with Bitcoin, we're discussing a couple of them. We have a couple of like Bitcoin specific requirements that might not apply to other blockchains or other use cases. Like how close to a use case is this IETF standard for Frost? You still there?
Maybe she's just not there.
She's muted, or
yeah, at least she's muted. Yeah. So if you can hear us, you're muted. But if you're gone,
yeah, okay,
no worries.
We'll move on otherwise.
But I can share the link here. Maybe you can add it to the
yeah, definitely,
to the reading list.
Okay. And of course, you can do nested MuSig within Frost and nested Frost within MuSig, but from a Bitcoin's perspective, that's gone off.
Yeah, I mean,
but it makes sense
we don't know
perspective to finalize MuSig first,
yeah.
And then work out how one might nest with the other or vice versa.
I really need to stress that we believe we can do this, but we really don't know. So I think I could write down a scheme, but I don't know if it's secure. We would need to prove it's secure, and nobody has done that so far. So I wouldn't recommend using nested MuSigs. at the moment.
Okay. So let's finish off then with libsec-p. So another, I don't know which is priority, finalizing the MuSig2 bit or getting a release of API out for libsec-p. What's your current thinking? Obviously, there are other contributors, other reviewers, other maintainers, but like, what's your thinking in terms of how close we are to having a libsec-p release? And yeah, API and formal API.
You mean you mean MuSig2 and libsec-p?
No. Like, I'm assuming
You
MuSig2 won't be in that first release.
No.
Or
I hope
you think it will be. Okay.
No.
Okay.
I really think I really hope we first have a release.
Okay. So these things with this like externally pub key issue needs to be solved before there'd be a libsec-p release. And any other things that need to be finalized in terms of that MuSig2 bit.
So yeah, I think the roadmap for MuSig2 is at the moment we're making changes to the BIP. As I said, it's mostly there. There are some final issues, mostly related to the DX only things where we need to do some changes, and we need to have some writing changes, but those can always be done later also. But once we really are confident about the algorithms that we have, we can update the implementation in libsec-p CKP, or we can do it on the fly even. So, and I need to say here that the current implementation based on an earlier version of the BIP draft is not in libsec-p, but in libsec-p CKP, which is a fork of this library maintained by Blockstream, where we add a few pieces of functionality, mostly relevant to our liquid side chain. But we also use it as a test bed in a sense for new developments. That's why we added MuSig2 first there. Probably we will first, once we have the BIP finalized, we will first update the CKP implementation to match the finalized BIP then. And when I say finalized BIP, I mean at the moment it's a draft, right? It's not even proposed, I think. So we need to get the BIP number, really read out for review, and maybe there are more comments and we need to update things. But the plan is then to update the implementation in libsec-p CKP, and then once that is stable, I really want to see this in libsec-p. There has been discussion about the scope of the fork and the library and so on, and I tend to believe that things that are related to, that are useful to the wider Bitcoin ecosystem should be in libsec-p. And I believe MuSig2 is useful to the wider ecosystem, so we should add it there. At the moment, it's maybe nice in libsec-p CKP because it's easier for us to get things merged and easier to play around with it in a rather experimental state. But once that code is stable, I think we should add it to libsec-p. Yeah, right. This is the issue. Yeah.
The libsec-p ZKP repo is, I mean, other people are using it. Is it designed to be a repo that other people use? I suppose if you've got experimental on the things that you think are experimental, it's kind of user beware type thing. But I mean, like, would there be a release for the ZKP repo as well at some point in the future, or is that kind of more geared to just using? That's kind of predominantly for elements liquids. But if you use it, it's kind of user developer beware type thing.
That's a good question. I think at the moment it's a little bit of both, and that's why I started this issue and this discussion. Or actually, I mean, the discussion was there before and more informal channels. If you ask me personally, I think what I'd like to see is that in libsec-p we really have the things for the Bitcoin ecosystem. In libsec-p CKP we would have things for the for the elements ecosystem or in the liquid ecosystem. And if we have that kind of separation, then the separation would be clearer. And then I think then it's possible to give a clearer answer if we want to have a release in libsec PCKP. So far, we haven't talked about this at all. Maybe then we wouldn't need a release, because anyway, it's used by mostly by this elements and liquid ecosystem, which we mostly control. But now that I say that, when I think about it, it's not even true, right? Because there are hardware wallets that support liquid. They use libsec PCKP. So I guess whenever you have a library, releases make a lot of sense. And so the truth is, so far we were too lazy to put out a release for libsec P. We should do this now. And maybe that's a good starting point then to think about the release for the CKP library too, independently of whether we move MuSig2 to the other library or not. Yeah.
Yeah, it's hard. It's a lot of grey areas here.
Yeah, and
there's no way to draw the line. Like, I suppose there's like the features type things, like which features should be in which libraries, if any. Well, if a feature should be in DKP or SecP or neither.
Right. Yeah.
And also like how much time like the maintainers, including yourself, can.
Right. I think this is one of the yeah. And I think upstream, I mean, the discussion in SecP is much more interesting in that respect, right? Because there we really have a community project there. And we want to have the things there that are relevant for Bitcoin, I think. But of course our time is limited. Whereas in the CKP fork, in the end, it's a repo controlled by Blockstream, right? We could do whatever we want with this repo. That's why I think we don't care that much what we put in there, but maybe we should care a little bit more and have the discussion with the upstream repo. And then it will be more meaningful for everybody.
Okay. There was some discussion on meaning of reusing some find the link. I don't know. But there's I mean, I'm assuming you're thinking like long-term, like, I mean, you've discussed like some cross-input signature aggregation type proposals. You're on a podcast recently talking about signature path aggregation. There's some things that can kind of be reused, right? And you're kind of having to, I can't find the link, I had it somewhere, but you're having to think like, okay, not only is this code potentially being used in the use case that we're coding it up for, but it might be used in future. I mean, it's not consensus, so it's not cemented like on the blockchain, but I suppose you're kind of trying to think ahead and making sure that it's modular, and a particular module could do the same function for both use cases.
Yeah,
even long-term things.
I think, yeah, it's always hard to predict the future when you're writing code, right? But I think maybe not yet at an implementation level, but at least at a specific, or at the level of writing papers, we're thinking about this. So if you really talk about if you mention cross-input signature aggregation, there's the link.
Yeah.
This would be it's kind of a different beast. It's not multi-signatures. It's from a theory point of view, it's a different thing. And it turns out that you could use something very similar to MuSig2, probably. Again, probably we need to write a paper about it and prove it's secure before we can be sure. To do cross-input signature aggregation. But we are not sure about whether this is the best approach even. if I remember correctly, our most recent thinking about cross-input signature aggregation is that actually, if we want to propose something like this, then the resulting crypto scheme would look more like the original Belaren in fact, than MuSig. Because this is a little bit more easier to prove secure probably, and it's more efficient. Yeah, I think in that setting, Belaren would be better, or variant maybe of Belaren. And if you think about it, the difference of in cross-input signature aggregation is really that. So what's the idea? You have multiple UTXOs. You're spending them all together, or you have different parties controlling them. Even they run an interactive protocol and want to spend them all together in a single transaction with a single signature. But if you think about it, now you have all the public keys on the chain. Whereas in MuSig, you don't have this, right? In MuSig, you have a taproot output, which is an aggregate key, aggregated from multiple keys, but you don't see the individual keys on the blockchain. But here you see them on the blockchain. And this is exactly what makes Belaren work in this setting, because as we discussed earlier, in Belaren all the individual keys go into the verification algorithm. So you need them. But for cross-input signature aggregation, you have them. So you could use Belaren, and that you probably wouldn't use it exactly, but do some minor tweaks to it. But at least it's a candidate there. Now that you show this issue, I didn't really read this posting. Yeah, I think here Russell is assuming that we would use something like MuSig2 for cross-input aggregation, but yeah, this is over a year ago. I think, yeah, as I said, our current thinking is that we would rather use something like Belaren. I think Jonas mentioned it here even somewhere in this discussion.
It's not critically important, right? Like it's just like a nice to have type thing. I mean, it's not
What exactly?
Well, this like long-term forward thinking, what can be reused for what? I suppose if you're doing a bit, then you don't exactly want to go through the hassle of having to change the bit.
Yeah, no, it's exactly how you say. I mean, yeah. I mean, you can think about when you're writing code at the moment. Of course, you can think about future applications, but it might just. And it's probably good to think about it, but it might turn out that in a month you want to do it differently. So, yeah, I think that's how it works. Yeah.
Okay. I think we're close to wrapping up then. I suppose roast. Should we finish with roast? So roast. So yeah, perhaps you can explain roast. I think Elizabeth briefly discussed it in her presentation to recently. You can't. So roast is on top. Is a protocol, a code on top of, like a wrapper on top of Frost, right? Like what specifically are you concerned with RE Frost to want something on top of it to not be susceptible to certain things?
Yeah, so the thing is that if you so let's say you have some threshold setup. I think the example I use mostly here is 11 out of 15. So you have an 11 or 15 setup, and now you want to create a signature. So you need 11 people. The problem with Frost is that you need exactly 11 people. So you really need to commit on the exact subset of 11 people that you want to use. And if it turns out that one of these signers in this set is offline, or turns out that really the signer doesn't want to sign, then you have to restart the protocol from scratch. So you need to pick another subset of 11 signers. kicking out maybe that one signer that was offline and replacing it by another one. But then again, you have to run it and could fail again and then fails again and so on.
You have to decide. So you have to. I don't understand that. You have to decide up front. If it's an 11:15, you have to decide up front when you start the protocol which 11 signers are going to be signing. So then if one doesn't sign, then you fail and you have to start again.
Right. Yeah.
Right. Okay.
And Roast gives you a clever way. I mean, you have to restart, but Roast gives you a clever way to restart in a sense, so that you don't need too many sessions at the end. So you know, maybe I have to start a few protocol runs of Frost, but I do it in a clever way such that I don't have to start too many of them. And I also and then another nice feature is that the resulting thing, what Roast gives you then is an asynchronous protocol in a sense. So you can always make progress. You never need to have timeouts. For example, in the simple approach that I just described here, you start with 11 and then maybe 10 of them reply, and you have some signer 11 that never replies, and it's just not clear, right? Maybe network is super slow and at some point it will reply, or it will just never reply. But if you do this naively, you would at some point you would need to raise a timeout, and maybe then you're wrong because you raise a timeout and then a second later the message arrives. And then you would have aborted, but actually the guy was there. And Roast avoids this because it never aborts sessions. It just starts new ones. But it never needs to abort existing sessions. So kind of it works by starting one session and then at some point after a few people replied, you start already a second session. And then either the first session can complete or the second session. And then if a few people respond to the second session, you may even start a third session and so on. But you leave them all open, and so that you never miss a message. You never kick out somebody because he appears to be offline, so you never need some kind of timeout. And this is just useful in real networks because timeouts are difficult. You never know what the right value for a timeout is.
The parties of the 11:15 on Liquid are expected to be online all the time, right? So it would be a surprise if I suppose it's just a hard decision, right? If you've got 15 parties, why choose a specific 11 of them? Like it's kind of why not? Why would you ditch 4 of them? Like there's no reason to if they're all equal parties.
You could, for example, just pick it. Yeah, I mean, either you're on Roast, but even in Roast, you have to. I mean, all Roast does is start Frost sessions, right? Because and it needs to start a first session, for example. And for these first sessions, you need to make some choice. You need to pick some 11 for which you do the first attempt. But yeah, you could just randomize it. Take a new random selection every time, for example, or always take the ones that responded quickly in the past. That's another totally meaningful strategy. But I guess you would want to have some randomness involved, because if you always pick the same 11 and they always work, you would never notice if someone fails, right? You maybe another signer, one of those 4 that you don't pick, it goes offline. You wouldn't even notice. Yeah, of course. I mean, you would notice because the TCP connection drops or something like this. But I guess you want to have some randomization to make sure that everyone is picked from time to time, just to see if things are working. But yeah, this is mostly just an implementation detail, I think. Anyway,
if it could,
if people are interested in Roast specifically, I gave a talk about that, which is also on YouTube.
Oh, okay.
You can also post the link. Maybe you can add it to the reading list.
Definitely.
But go ahead. Sorry. You wanted to.
We were discussing before about changing it from 11 to 15, so like 11 to 16 or whatever. Like adding, I can't remember what the term you use for like Liquid members, but like if that's going to change regularly or semi-regularly, suppose ideally you want to avoid. Ideally, if you could avoid that on-chain transaction, you would. But it sounds like you can't do that. You would need an on-chain transaction every time.
Right.
Of
But-
Liquid.
But I don't think that's a big deal because you anyway.
It hasn't
Yeah.
changed. It hasn't changed for years, right? Is it still the same 15 that it's always been, or have they been swapped in and out?
I
don't
think
know.
they haven't been swapped in and out,
Liquid's
but I think I'm just saying it's not a big problem to make on-chain transactions because they do on-chain transactions all the time when they do payouts or packouts from the Liquid network. So doing an on-chain transaction really isn't a big of a deal, and even if you wouldn't do it constantly, I mean, how often do you add a member to this 15? Maybe once in a month or so.
I don't know.
I guess
I have no idea how it works.
Yeah, at the moment
it's 11:15, but I have no idea whether parties have been swapped in or out. It doesn't seem to have changed.
No.
From 11:15
Yeah,
years.
the thing is, we are adding more people to the federation, or more members to the federation, but at the moment we are not adding more members to this set of signers just because we've committed on this 11 or 15 thing because of some specific reasons how multi-sigs currently work in Bitcoin. So if you go beyond 15, it will be more inefficient, and then Roast would, in the long term, maybe give us a way to scale that number without losing efficiency on chain.
But the 11,
But
the 11
even in then
signers-
setting, if it's easy to add people, I think we wouldn't add a new member every day, right? So, and even if you do it every day, one transaction per day, that's not that expensive.
Not currently. We don't know what the fees will be like.
Okay, right.
Yeah. Back to 2017 fee levels.
Yeah, at least at the moment it's okay.
Yeah, at least we don't care about that.
Yeah.
Is it currently randomized in terms of choosing the 11 to 15 in just the normal check multisig? How the 11 decided on who's going to sign?
That's a good question. I'm not sure. I think at the moment, but I'm really not sure. I think at the moment it's just that we have a rotating leader and this leader rotates, and the leader will ask everyone else to send a signature, and then we just take the first 11 signatures that we get and put them on the transaction. So at the moment, so this is the kind of it uses this naive Bitcoin multisig or naive Bitcoin threshold sig, and this is exactly where it's better than Frost in a sense, because it with this approach you don't need to pre-commit on which 11 exactly you want to use. You can just ask everybody for their partial signature, and you wait until you have 11, but you can ask every one of the 15 members. So we can just take the first 11, or I don't know, maybe we wait for a second longer and then randomize it. I don't know, but I bet we take the first 11, but I would need to read the code or
I'm assuming
ask people who know more about Liquid.
I'm assuming it still uses check multisig rather than check together. The benefit of using check together wouldn't be, I don't know, it's probably not worth the hassle currently.
Yeah. I don't know.
Okay.
I would need to ask the Liquid engineers.
Yeah, Liquid guys. Okay, we should wrap up because my brain needs to rest. Any final questions from anybody on the call? I'm monitoring comments as well. If anyone has any questions in the comments.
I do have a quick question.
Go for it.
Cool. Yeah. In MuSig, back in MuSig land, in the BIP, there's a section called verify failed test cases, and it provides some signatures. One of them exceeds the group size and it fails. One of them is the wrong signer, and so it fails. And one of them is the wrong signature, but why is that an important test to make?
That's a very specific question.
Oh yeah, I can hear. I'll throw something in the chat.
I've got it up on the screen. Like where is it?
So in the test vector file. Now, just yesterday we converted that to a JSON file.
Yeah, I threw in the chat the JSON file. So.
Oh yeah. So the reason is we really want to. We want to have a specific property in signatures. So there are different security notions of signatures, and in theory, what we usually expect from a signature scheme, even without multisigs, just from a single signer normal signature scheme, is some unforgeability notion, right? Which means that you can only sign messages if you have the secret key. And there are various forms of unforgeability, and what I just described is weak unforgeability. But there's also a strong unforgeability, which is a little bit stronger, as the name says. And it says you can't even come up with. So let's say I give you a signature on a specific message, and then you can't even come up with a second signature, a different signature on the specific message. This is strong unforgeability, and if you wouldn't check for the negation, then you could easily do that. I sent you the signature and you just negate it and you had a different signature. It's just negated, but it's different. And there is the reason why we want to have the strong unforgeability is mostly just because we can have it. It's there. And maybe have you ever heard of malleability issues in Bitcoin?
Yeah.
This is specifically also related to this because this is one source of malleability. Now, before, it was before SegWit when signature data was so in SegWit signature data became witness data and didn't from SegWit on it doesn't influence the transaction IDs anymore. But before SegWit, this was in ECDSA. This was one source of malleability because in ECDSA you could do exactly this. So ECDSA signature is like a Schnorr signature is 2 components, and you could just negate one of them.
To be clear, just for me, for the negation, is that multiplying the whole point by -1, for example, or is that mirroring it on the other side of an axis? Or what does negation actually look like as if it were to be performed?
Good question. I'm not even sure what exactly is negated in this test case, but if you look at the Schnorr signature, it basically has 2 components. It's a group element, so point on the curve, and it's a scalar. And the scalar is, in a sense, an exponent, so something like a secret key. And you could negate either. Now BIP 340 makes sure that no matter what you negate, it will always be an invalid signature. But in general, it's possible to negate the point, or it's possible to negate the scalar.
Okay, cool. Thanks. I'll play around with that and see what I find. Thank you.
Yeah, maybe look into the old ECDSA specification because this really had the problem. And you can see how the negation was ignored there, and this resulted to the fact that when you have a negation, you negate one of the components and then you get another. You have a signature, you negate one of the components and you get another valid signature.
Thank you.
Yeah, I went through the Schnorr test vectors a while back, and Peter said negated means taking the complement with the group order n. The signature won't be valid if you verify it using the negated message rather than the actual message used in the signature.
Yeah, this is then negating the scalar, I think, what Peter is talking about. Yeah.
Is this not the same thing that Grant's asking about? No?
No, it is the same thing. I'm just saying, there are 2 things you could potentially negate, right? It's because Schnorr signature has 2 components, R and S, and you could negate R and you could negate S. So
okay, gotcha.
It's a very weird question when he asks what is meant here when it says negated. To be honest, I don't know. I guess S has been negated, but the comment here doesn't really say it.
I see. What's been negated in this MuSig test vector?
Yeah.
Okay, cool. Any other final comments, questions? Anyone on the call? No one on the comments? Okay, well, thank you very much, Tim. Thank you, Elizabeth, for joining. Thank you, everyone else, for joining. I'll
Yeah,
get a
thanks
transcript
for
up. Yeah,
thanks
no
for
worries.
joining. Yeah,
I'll get a transcript up.
thanks for
and
inviting me.
I'll collect the 2 or 3 links that you put in the comments and add it to that reading list. But yeah, thank you very much,
Great.
everyone. Good night.
Thanks.
Thanks.
And stream.